Hello, everybody. My name is Ashad, and we have Arno Schödl today. So we'll be talking about stuff such as error handling, exception handling, topics that are exceptionally, I guess, complicated in C++. So there is a way to abort your program, there is a way to send an error code, there is a way to throw exception, but somehow still a lot of code bases kind of ban it all together. And we still have, I guess, most of the compilers having a flag for you to disable exceptions in the entire STL thing. So Arno is coming from a real world of production software, and he definitely should know how we should do it right in a proper program. So I will forward the mic to him. But before I do, I want everyone to know that there is this online discussion that's taking place in parallel with every talk, so you can ask your questions there, and then Arno will be happy to answer to most of them, I guess, after the talk or in the Zoom discussion after the talk itself. Arno, to you.
All right, thank you very much for the intro. And yes, so I'm Arno Schödl. I am from ThinkCell. We are really doing PowerPoint add-ins, kind of fancy PowerPoint add-ins where we hack around PowerPoint and use some smart algorithms to do automatic layout. But that's not the topic for today. Today, I want to talk about something which actually kept us awake at the very beginning when we started the project, and that's error handling. Now, we somehow had to find out how we would deal with errors in our production code. And over time, I think we evolved a pretty interesting approach of how we actually deal with errors in the program. And that's what I want to share with you today. Now, well, as you all know, errors can happen anywhere, right? And we always want reliable programs. The customers hate it if things don't work. But at the same time, we actually have no time at all to write any error handling code. And now the question is, what do we do? Before we go into this, I want to start a little bit with the basics. Where do errors usually come from when we write C++? So let's say we have a file here. We open a file with a particular file name. And what happens if that file doesn't exist? Well, the earliest, simplest version is probably a return value. So that's, say, in the simple case, you get a Boolean back whether things worked or not. Of course, first of all, you have to check it, right? And second, this doesn't work for constructors. From constructors, you may want to have an out parameter to transport the error out. Both not particularly pretty, but if you want some value out without any exceptions, that's pretty much the only way. Both clutter the code with checks. In case of return values, for newer C++ versions, you can at least use no discard to make sure that your error code is checked in the calling code. Now, another option is, which is actually quite convenient, are status flags. So the way this works is you have a single control path. You just execute whatever you want to. You make the calls that you want to call, and as soon as an error occurs, some status flag is set. And you then later on, once you're finished with everything, you query the status flag. That of course is good if checking at the very end is good enough. When you're writing to a file, for example, it's great. Often it's also used when you're writing to a graphics card, when you're issuing graphics calls. Also there, you just render all the triangles, and at the end, you check whether your graphics card died in the middle. If you need the intermediate results, like when you're reading a file, maybe it's not such a great idea. It is the default for C++ I/O streams. Of course, C++ I/O streams themselves kind of fell a little bit out of favor now that we have stiff format. But, well, they actually use status flags. Another way to report errors are monads, a little bit more modern. It's kind of a similar idea. You want the same code path for success and the error case. It's a little bit like you're packaging the actual result with an error. It's like a variant between the result and an error, plus a bunch of utilities to transport this data type through your program. There is for C++ 23, there is a proposal still expected, which is doing that for C++. It has now, last time I checked, it has reached revision 11, that paper. So it's been actively worked on, and I probably it'll make it into C++ 23. And if not, then surely the next version. Now, and then of course there's the standard way to report errors, which are exceptions. Before I want to go a little bit about into possible pitfalls when using exceptions. You should always catch them by reference. If you don't, then you may get slicing. That is, from a derived object, you kind of slice off the base class, which is normally not what you want. And also, if you don't catch by exception, then that exception object will be copied, and that might by itself will trigger or may trigger an exception, which will then be a double throw, and that will terminate your program. Certainly not something you want. Now, so here it's called by value, but you actually want to call catch it by exception by reference to avoid these problems. One more thing to bring up here is that if you are rethrowing an exception with throw, then this will actually throw the original exception. I didn't know that for a while. That's why I bring it up, so that this throw will basically resurrect your original exception object, not the one that you caught. So if you sliced, then you now have a copy, but the throw will actually throw the original. Now, exceptions are, well, some people criticize them. They work a little bit like a multi-level return go tool. They kind of break up the local control flow and add code paths to your program that you kind of all have to account for when designing your program. So they do add complexity. And because these throwing locations are not annotated, you also don't really see where these code paths come from. They may come from anywhere. So here, when you have code like that, you have a function main that calls a function increment, and for I equals 3, it will throw. Then and that throwing will then be thrown out of the call to increment, which will then be called in main. If you have kind of that kind of setup. Here, these are extra code paths that you have out of your increment function and in main. So you could kind of simulate that with gotos. So here you would have the secret out parameter, I call the PSC exception, and whenever you throw an exception, you set that out parameter, and then with a goto, you jump to the end of your function and exit somehow. And then outside in the caller, you would have this secret exception variable is then kind of checked, and again some goto is invoked into the catch handler. Of course, it's a little bit contrived, but that's effectively what's happening. You are adding these extra control paths, execution paths that add complexity that you may not want. Now, of course, you may say, well, what are you whining about? Of course, we must write exception-safe code. Now, exception safety, I want to talk about it briefly. There are what's called exception safety guarantees. And it's not really about exceptions. It's more generally about failures in your code. Whenever a failure occurs, what are the post conditions that you can expect from that failure? Now, and really these things are part of your function specification. When you're writing a function, you have to decide how am I going to handle failure cases, and what kind of guarantees am I going to make about the state of the system after that function failed. Now, in the best of all worlds, of course, your function never fails. That's the strongest guarantee you can give, and it's certainly very desirable, but it's unfortunately not always possible. Now, the next best thing you can have is the strong exception guarantee. The strong exception guarantee means that the function may fail, but if it fails, it will restore the program state to whatever it was before. So it's like a transaction. Either the function side effects will take place, they will all get executed, or none of them get executed, and you have the state that the program had before. Now, in library functions, that's certainly very desirable, and our library does it, our in-house library, the standard library does it, and there it's actually not so hard to do. For general application code, where you have many state changes in a sequence, it's very hard to do because it probably means to keep track of all these state changes and to roll them back without triggering another exception if something goes wrong. So If that's too much to ask for, you may aim for the basic exception guarantee. That basically says, okay, we can fail, but if we fail, we don't guarantee that you actually get the state before you call that function, but you may get any valid state, any valid program state. So the question is, how useful is that guarantee really? So imagine, someone calls Microsoft support and says, hello, is this Microsoft Word support? I'm writing a book, and suddenly Word deleted everything. And then Microsoft says, well, that's actually fine because Word only has the basic exception guarantee, and an empty document is a valid state. And then the customer says, oh, that's great. Thank you very much for the explanation. I'm very happy. Very unlikely to happen, right? So it's a little bit the question, what does that actually buy us, this basic exception guarantee? So here's the challenge. Error handling is a lot of effort. In development, you really have to be very paranoid. We have to watch out for anything that could fail. And then we have to create a lot of extra code to accommodate all these things that can potentially fail. And then in testing, we have to test all these code paths that we generated, all this extra code, because we know that if code doesn't get tested, it likely won't work. And at the end, after we did all that, so the developers put in a lot of effort, the testers put in a lot of effort, at the end, we have very little customer gain, because the customers pay us for doing actual work, not to write beautiful error handlers. So the question is, what do we do? Well, I can tell you what we did. And here's what we did. So first of all, you check everything. So every API call you make, we have some wrapper around that API call that checks for errors. On Windows, you may get a bool returned, and then you have to check get last error, or you have some comp functions, they return H results. On Unix, various Unix flavors, macOS or Linux, you have Arno. So for all these things, you have wrappers and you check. You have lots of certs in the program. We actually leave them in release. So we ship the program with the certs, and we have aggressive asserts that check whether the program is still in a valid state. And developers are encouraged to write many asserts. The functions which are not expected to throw exceptions are marked no except. Why? Well, simply because then we have an early way to recognize if such a function actually still threw an exception, then its terminate would be called, and we can set a terminate handler that actually will deal with that exception and know that something's wrong. Now, of course, that means that any function that is not supposed to throw an exception but does anyway is going to terminate the program. But if you throw an unexpected exception, your program is probably going to terminate anyway. So not much harm is done there. After we've done all that, we added all these checks. We check all the API calls, we added asserts, we made sure that no exceptions that shouldn't be thrown are flying around our program. We assume that everything works. We don't write any error handlers. And then, so the goal to do that is we want to keep the set of code paths small. As I said, all of these error handlers add a lot of code paths that you have to test, that you have to develop, and that's costly. And the goal is here, keep the set of code paths small, and more importantly, keep the set of program states small. So if things are assumed not to fail, then your program doesn't have to accommodate all the states that would actually come about if certain things don't work. So very likely, your set of program states becomes smaller, and it becomes much more much easier to reason about your code. So that's certainly nice. But of course, the checks will fail, right? So some things will fail quite predictably. For example, the file name may not be there that the user wants to load. That's certainly an error that we have to deal with. Some other checks may fail unexpectedly because the operating system behaves differently than what you expected it to behave. Now, what do we do? In this case, priority number one is collect as much information as you can. So it's not necessarily to keep the program running, it's collect information. That means for our client code that runs on a client machine, we send a report with a mini dump, with a memory dump. We send that home to our server to collect data. In case of our server, we actually halt the thread. We stop the thread so that an operator can attach, a developer can attach himself or herself to the server and analyze the problem. Because there's nothing as easy to analyze as a live system. You can look into every variable. You can do everything much easier than having to deal with a mini dump. Now, only priority number 2 is to carry on somehow. So if the check was critical, and most checks are, if an assertion fails, that's assumed to be a critical assertion. You did not design the program for that assertion to be violated. Again, with the API calls, if you don't assume that they fail, the program is not designed to work when these API calls fail. So in these situations, even if we now carry on, the program behavior is now undefined. So we don't know what's going to work and what's not going to work. So we don't send any further reports. Anything that happens from now on may actually just be fallout from the previous error. So we don't want to hear from this program again. Basically, this program went over the cliff. It's now undefined, and that's it. That said, if assertions fail, we don't terminate the program deliberately, because experience shows assertions can be wrong. So if we encourage our developers, if you encourage your developers to write aggressive assertions, then these aggressive assertions, you want them to be aggressive because you want to find things out about your program. You want to be notified if things don't go according to the developer's expectation. But writing these asserts, mistakes will happen. And if you terminate the program when the assertion fires, then you just penalize the poor developer for terminating the program, for writing the assert by terminating the program. So the customers will come and say, hey, why did you terminate my program? And then the developer realizes, I just made a mistake writing that assertion. Next time I'll know better. I won't write assertions anymore. And that is not exactly what we want. We want to write aggressive assertions. So we don't terminate when assertions, when an assert goes wrong. Now, if you need safety, like you are controlling nuclear power plants, right? You need to add this safety at a higher level. You need to make sure that your program doesn't do stupid stuff. And so you can scram the control rods, for example. In our case, it's not quite as bad, but the server may actually, halt threads. And it really doesn't matter whether the error handling halted the thread or whether the server just went into an infinite loop. In any case, there are basically threads disappearing, and they're just never coming back. They're never available for dispatch again. And in this case, our server will recognize it, will categorize the requests in certain categories, and it will stop responding to the kind of category where we actually got too many errors. So, yes. Once we did that, once we have collected all this information and the error reports have been sent home and they're available for us for our analysis, the next step is we want to reproduce the error at home. We want to know what's wrong, and knowing what's wrong basically means you need to reproduce the error. You need to be able to recreate the error in your lab. And once you've done that, you add handling code only for the errors that are actually reproducible. Reason being, if there's an error that may be quite frequent, but that they cannot reproduce and you don't really know how it comes about, it's hard to check whether your error handling is actually effective. You can write something, but it may or may not work. And if you recreated the error, then you can actually check it. You can test it, and that's much better. And yeah, experience shows if you don't do that, if you just blindly write error handlers, you write many handlers that are never used, or they're used and just because they have never been tested, they just do the wrong thing. Now, again, having done that, 5% of the handlers handle 95% of the errors. So the goal here is don't write error handlers for all errors. There will never be perfection, and some errors just stay unhandled. But by putting effort into writing the error handlers that you really need, the errors that are really frequent, you can still increase the reliability of your program beyond what you would actually be able to do if you just sprinkled your error handlers all over the place. So the key here is you want to write good handlers. It's bad to just show the error message box. It's good to actually fix the problem. We had one situation where we used the XML component of Microsoft Windows for XML parsing early on in the stage of the project. And it turned out that sometimes this XML component didn't work. And so we got these error messages. And instead of just saying, sorry, your XML component seems to be broken, we actually figured out that by re-registering the component in the registry, we could actually fix it. So what we did is whenever we encountered the error and the XML component wasn't there, we just re-registered it. And we actually fixed the error, which was great, because then we didn't even have to deal with the situation that this thing wouldn't work. It would always work if we just had a chance to re-register it. And that's really the best error handling you can do, that the error that doesn't even make it up to the user, it's just invisible, it just gets fixed. And there are quite a few of these error handlers in our code. And that really makes a difference in reliability. I want to go through some categories of errors, which are that we kind of came up with in the course of the project. The simplest one, of course, is the critical error, the one that would essentially break your code, where you say, oh, behavior afterwards is undefined. So that's kind of things like a null pointer access, an API call that is not expected to fail, or even that is not expected to fail with this particular error code. So you may allow certain error codes because you understand them, but others not because you don't understand them. Even that's then a critical error. And of course, also failed assertions would also fall under this category. Now, as I said, they are basically in the category, this never happens. So there's no handler for it. And it's a bit like C++ undefined behavior. The program is invalid afterwards. You're not sending any more error reports. You just assume that the program is broken. Now, what do you do if these kind of things occur? Well, the client sends a mini dump and disables the reports. So the server actually notifies the developer and stops the thread so that you can attach a debugger. Should you notify the user? Well, we only notify the user if a false alarm is unlikely. Again, assertions may be wrong, and you don't want to penalize anyone for writing bad assertions, because then they won't write any assertions anymore. So we only notify the user if we are reasonably sure that this is not a false alarm. So in case of an API call that's failing, it was probably a good reason we made that API call. So in this case, it's actually pretty likely that kind of things will go south. So we actually notify the user. If it's just an assertion that went wrong, we don't notify the user. So like you have to exercise some judgment there. Here's another category of errors that's like one level down from critical. I would call it untested. Let's say you have a register foo in the operating system, and that registers foos. And we want to know all the foos that got registered in our program. So we install a hook that the register foo hook, and that executes the original register foo, and then keeps track of foos inside our program if that register foo succeeded. Now let's say, of course, if the register foo failed, then there's really nothing for us to do. So quite naively, this program looks correct. Now the problem is, what if we don't have any reproduction for register foo failing? Then probably if register foo out there in the wild on the customer machine suddenly starts failing, this may be an interesting scenario. And the user may call later on and say, something is wrong with my machine. And then it would be nice to know, well, is that something where we previously, before there's a crash or some bad behavior happened, we saw something that wasn't quite expected. So let's say we have no reproduction, then we probably still want to know about this problem. Let's say, so what do we do in this case? For clients, we send reports. In this case, we don't suppress future reports entirely because the program is still in a valid state. I mean, we think that we actually wrote the right code for dealing with a failed register foo, but still we want to know about it. So since register foo may be called very often and it may fail each and every time, then that would generate an awful lot of reports that is being sent to our server, and then of course the client would grind to a halt because it's only busy sending reports. Now we don't want that, so we throttle them. We just say, well, if there are too many coming, we'll start suppressing reports. Now in debug, if this problem happens, then we are actually in a very lucky situation because so far we had no reproduction. And if you encounter this problem while developing at home, then we suddenly may have a reproduction. You may actually know what you did in order to trigger it. And in any case, you still have a live system where the problem occurs, so you can analyze it. So in debug, you certainly want to pop up an error message saying, hey, developer, we ran into this interesting scenario that we always wanted to know about. You may want to take a look. Now the server, again, sends a report. It does not halt the thread. Okay, here's another one. The bad user experience. You may have something like a third-party bug. Like, for example, PowerPoint suddenly makes shapes disappear sometimes. This may all be reproducible. So we've tried it at home, and yes, PowerPoint shapes disappear, and it's supported. We somehow deal with it. We tested it, and things that still survives. And but still, it's probably something that the user does not appreciate, right? So suddenly shapes disappearing. So what do we do? In this case, the user may complain, right? The user may call and say, hey, you're making shapes disappear. And in this case, we would like to tell them what actually happened. So we actually only log this situation. And we don't send any report because, well, this report wouldn't buy us anything because we already know that the situation can arise. So we log it, and so that when the user calls, we can look into the log and explain the behavior. If this occurs very often, then you may decide, well, we have to do something about it, right? We may have to repair the situation or write an actual error message for the user. But if it just happens very rarely, this may not be something that you want to do. You may think, well, my time is better spent elsewhere. But still, what you can do is write a simple statement in the program that makes sure that that situation actually gets logged. Now, here's another one, the indication of a broken environment. So it can happen, for example, that we are running as an add-in in PowerPoint. So we are living inside the PowerPoint process as a dynamically loaded library. And maybe another add-in does the same. It's also running as a DLL, and we are hooking functions, and that other add-in also may hook functions. So, and it may so happen that we both have hooked the same function. That's fully supported by us. We should be okay with one add-in hooking over the other add-in. That's fine. But the other add-in may not be ready for it. So still, it's something that we may want to know about. And there's another example for here is if you set the decimal separator in the operating system and you decide, well, maybe the point or the comma is not good enough, I would like to have a space as a decimal separator. Well, of course, you can do that, but that's so unusual that some programs may not be able to deal with it. So, and that there may be some downstream problems with it. So that's again something you may want to know, because it could be the cause of a problem. Now, if you're running on a machine during remote support session, so you have a support engineer attached to the customer machine, and he's looking at the problem because the customer called. You probably want to know let the engineer know that something unusual is happening on the machine that may be related to problems. So that's one reason to actually bring these things up. Logging them, well, is maybe not quite so practical, because if this is a permanent situation on the customer machine, like for example, the default separator is set to space, then you would just fill the log file. It would just become an awfully big log file that may not be feasible. Now, let's talk about what we do. I always said, okay, we send this error report to the server, right? And so what do we do with these error reports once they arrived at the server? I already explained to you, the developer looked at them and tried to recreate the problem at home, and then it's writing possibly some error handling code. But how is that exactly happening? What's happening when this error report arrives at our server? What we do is these memory dumps that are sent to the server, they're either sent automatically, or if the user said, no, I don't want you to send anything automatically, we also allow the user to send them by mail on a case-by-case basis. So if the user is really annoyed by a problem, she can actually send the error report by mail. These error reports then go into a database, and the memory dumps are automatically opened in a debugger. That's WinDebug on Windows, and that's the LLDB on Mac for Mac memory dumps. And then with the help of the simple files of our binaries, the errors are automatically categorized by file and line where they occur. And all that information is then written into the database. And then these details are then accessible to the developers. They can actually go through all the errors that occurred out there in the wild, look at how frequent they are, where they occurred, sort them by time, by which system they occurred on, which account, which license key they occurred on. So you can see whether certain things are possibly related to the environment of a particular license key or of a particular machine. So you can look at all these things, open the mini dump, the memory dump in a debugger, and try to figure out what went wrong. Now, once the developer then fixed the problem, they can actually mark the problem as fixed. They can say, well, starting from this version onward, I think that problem should be solved. And if we then have an update available later on, so later on this fixed version will get built and will get published, and once that version is published, then we'll actually can send back an automatic update to the user. So once the user ran into the problem, we'll just send back the update and say, hey, if you can fix this problem by updating this particular version, or if the user enabled automatic updates, the update will actually get installed automatically, and then things will get disabled and re-enabled, and everything will be good. This also works for email. So when the user decided to send the error report by email, she will actually get an answer by mail, which often seems quite magic, because people don't expect answers to emails to be quite as quick. So you can just send an email with the error report, say, hey, I have a problem, please fix this, and 5 seconds later you get the answer back, please update to version XYZ, which is quite nice. Okay, I want to talk about something else here, and that is the cause analysis. So a problem, as I already said, may be related to the customer environment. It may not be something that we could immediately recreate in in-house testing, because there's some component that is running on the customer machine which makes that problem more frequent or happen all the time. So the memory dumps that we receive from the users all contain a list of the modules which are loaded in the particular process. So the question is, can we somehow find out which one of these modules is actually related to the error, which one is causing the error? And the nice thing is, we usually have, for every error that occurs, we usually have many examples. We collect all these in the database, and so we can freely analyze them and try to crunch the data and hopefully find out which module is responsible. And I want to tell you how we do this. So we have a database, and that database has all the reports. And let's say we divide up this database into reports of a particular problem and reports which in practice have different problems, but that we can actually consider somehow a background sample of machines that don't have this problem. So we have reports that have this problem and reports that don't have this problem. And here I just said, okay, we have 12 reports and 6 of them have this problem, and I mark them as 1, and all the zeros are the ones that don't have this problem. Okay, now in addition, we have the information which modules are contained in these individual dumps. So you may have, maybe for simplicity, you have just a module A and a module B, and the module A occurs 3 times out of 6 for both the reports that have the problem and the reports that don't have the problem, while the module B has 4 out of 6 where the report has the problem, but only 2 out of 6 where the report doesn't have this problem. So you could say, well, maybe module B is somewhat likely to have to do with the problem. So let's see. Now, how would we judge this? How would we decide if module B could be responsible? And maybe there are other modules. So which one is responsible? Here's the approach that we took. So let's say we want to compress this string of zeros and ones. Which reports have the problem and which don't have the problem? So we want to kind of find a succinct explanation of the world, if you want to phrase it philosophically. So that comes down to compression. Now, if module B has to do with the problem, then the knowledge whether module B occurred or not should help us explaining the world. We could say, well, if you have module B, then you probably have this problem. And if you don't, then you likely don't. And that should help finding a succinct explanation, a succinct description of our error reports, whether they contain the problem or not. So how do we do that? Well, the compression that we're going to use is a perfect arithmetic compression. That's essentially the Laplacian estimator of the probability that a report has the particular problem. It's a very well-known technique that you use also for image compression or for many other things, where you are essentially trying to estimate, well, if something occurs very frequent, then maybe I can encode it in a shorter sequence, and if something is very rare, I want to encode it with a longer sequence of bits, and that way I will actually save memory. And initially, you consider in the standard estimator, you consider all the probabilities equally likely between 0 and 1. And if you do that and then run the estimator, you can actually the number of bits that are required if you want to compress n bits, and k of these bits are actually ones, the rest is zeros, is actually independent of the distribution of the k bits. It only depends on the number of bits and the number of ones, and it's this log n plus 1 times n over k. Now let's do some plausibility checks. The number of bits that you need becomes actually smaller if p is closer to 0 or closer to 1. So if you are still at 50-50, then you cannot do any better than just spending 1 bit on each one of these decisions. But if one of these decisions is much more frequent, then you actually can encode them in a smart way, and you will save some bits. So here, if you have 12 bits and 6 ones, you actually need 13.55 bits if you encode them with this perfect arithmetic compression. And as you can see, 13.55, that's more than 12, right? So you are losing, you're requiring more space suddenly, but that's inevitable. I mean, any compression algorithm will always, on some inputs, require more bits than it originally needed, and only on some well-behaved input it would actually compress. And that's the well-known pigeonhole principle. That's unavoidable. So, but here you can see kind of what we're talking about. So 12 bits, 6 ones is 13.55 bits. If we had no ones at all, it would actually be 3.7 bits. So we'd save quite a bit. Now, let's see if these modules, the presence of these modules can actually help us compress it. So as I said, if you compress all the reports together, 6 out of 12, you get 13.55 bits. So if we now make use of module A. And there we are kind of having an even number for reports that have the problem and that don't have the problem. Both have 3 times out of 6 module A. We would expect this kind of not to help, right? Because this doesn't tell you really anything about which ones actually have the problem, which ones don't. So, but still, let's try it out. So first of all, we have to say, for my predictor, I'm going to use module A over B. This is something you have to transmit. You have to, when you compress that sequence, you have to say, well, in order to help me along, I will consider module A. The recipient will know about module A, and it will also know about module B, but it won't know which ones you picked to actually help you compress it. So that's something you have to send along. So that costs 1 bit. Now then, compressing all the reports with A is 3 out of 6 have ones, and 3 out of 6 have zeros, and that costs you 7.13 bits. And then you compress all the reports without the A. And the important thing here is that we make the assumption that these probabilities, how often the problem occurs for reports that contain A or that don't contain A, are completely independent. So you have to kind of rediscover that it's 50% in this case. And so that's 7.13 bits. So you have to basically pay extra to do this rediscovery. And that gives you a total of 15.26 bits. And that's more than the 13.55 when you compress all the reports together. And that tells you module A has nothing to do with the problem. Of course, now the real question was, what about module B? Right? So there you have a bit of a different values. You have, first of all, you have this 1 bit again. You have to now choose B over A. And then you compress all the reports that contain B. That's 6.71 bits. And then all the reports that don't contain a B. That's again 6.71 bits. It's symmetric. So if you compress a sequence of 6 with 4 ones or a sequence of bits with 4 zeros, it takes just the same number of bits. And in this case, the total number of bits is 14.43, which is still not enough. It's still not enough to beat compressing all the reports together. So it's fair to say that we can still say, well, this is rather chance. We have no indication that module B has something to do with the problem. Now, if you go further and say you have a module C with 5 out of 6 versus 1 out of 6, what do you get then? Well, first of all, we have to choose module C. But in this case, we have 3, so it's C over A and B. So that's the logarithm of 3, and that's 1.58 bits that you now need to compress that information or transmit this information. And then you compress all the reports that have C. That's 5 out of 6. That's only for 5.39 bits, and 5.39 bits again because we have 1 out of 6 for all the reports without C. And if you add it all up, you get 12.37 bits, which is better than the 13.55 bits. So in this case, we would say, yes, module C probably or may have something to do with the problem. And in practice, we don't do this, of course, with 3 modules. We do this with many, many more modules. And we're not only going to do this with modules, we also extend it to module versions and certain version ranges. So from a certain version or to a certain version or in between 2 different versions, all of these, if you create these many more hypotheses, then it will get the chance that that you discovered something that's just chance is much more likely. Because you just try out many more things, and it's just by chance one of them may work. But that's being taken care of because you have to encode your choice. That's okay. And we are doing all that, and it gives us a pretty good idea of which modules actually have to do with the problem. And it's kind of nice. You can scroll through the error reports, and there's always a ranking of the modules that are actually that may be responsible. And that then if there's a third-party problem, if you have a virus scanner, or if you have another add-in, this very quickly pops up to the top of the list, and you know, okay, that's the problem, without having to go through many of these error reports and kind of find the correlation yourself. Okay. There's one more short thing I want to talk about, which are C++ 20 contracts. And So that C++20 contracts are a new language feature. They were supposed to be in C++20. It's kind of like an assertion on steroids. It allows you to declare certain function pre and post conditions and write them into the code in such a way that they're associated with the function. And the thing is, many of the questions that we discussed in this talk, of course, came up in the design of these contracts. So when should we actually check the contract? Should it happen on debug? Should it happen on release? Should there be some contracts which are never checked? They are just for documentation. You just want to write them into the code in a formal way so that you have that formal description somewhere, except just instead of just having a comment. Now, what do you do if a contract gets violated? Do you always want to terminate? My answer would be no. Do you want to carry on? Do you want to report? Like, what do you report? How do you report? To whom do you report? There were many of these questions, and at the end, that triggered the contracts to be removed from the C++20 standard because there was no consensus, no broad consensus of how these things should be handled. And this whole discussion will continue for C++23. All right, I'm coming to the end of my talk. Thank you very much for listening. And if you have any questions, go ahead. And yes, we are doing this because we are hiring at ThinkCell for the Berlin office. And so if you have any interest in coming to Germany, then you are certainly very welcome. And we would take care of all the details. All right, thank you very much. And yeah, I'm looking forward to your questions.
So we have a few questions, very different in nature. I guess one of them is about using assertions just in the debug mode. What's your viewpoint on this?
I think a good reason to use assertions in debug is, so in general, I mean, it is better to use assertions in debug than not to use assertions at all, right? I mean, assertions are always good. Now, what's the reason to only execute them in debug? Well, I think the main reason is performance. So we certainly also have the option in our system that if during profiling we find out that certain assertions will just eat up too much performance, then we'll switch them to debug only. And that's certainly better than nothing. But if I would only do that for assertions which are really eating into performance, the default is that they're staying in release.
On my own side, I'm wondering what's the state of contracts going into C++23? What do you think is like the main hurdle, and is there any chance we're going to get them? If we get them, what will be like the final solution like?
Okay, I must here very clearly say I don't know what the actual state, the current state is. So I know the professor who is a professor in Madrid. He introduced the paper. I'm not sure exactly what the current state is. So I have to pass on this one.
There is another question which is like EU oriented, so I guess you're well positioned to answer it. It's regarding the slides where you talk about the way applications write logs, stack traces, error messages into the local database on the machine. So there is a guy asking if EU laws require these automatic reports to be opt-in instead of opt-out.
I think in general you have to opt in. Like you have to at least ask. You can force an answer, but yes, you are required to ask for sure. I think whether the check mark is set by default or not set by default, I think it's kind of like a gray zone. So yeah, but certainly you have to ask, and it's not something where you can probably require that error reports are sent to you as a precondition for using the product, because it's not strictly required for using the product, so you can't bundle these things together. You have to ask. But I mean, still you can make it easy. And in reality, we've had this question from customers: what message or what did we see in these reports and these mini dumps? And these mini dumps are mainly stack storage. So they're basically there's no heap memory because it would be just way too much. And so in practice, I have never seen anything even remotely looking like user data in these memory in these mini dumps. So it's very unlikely that you'll get that the user will reveal anything. In practice, I've never seen it, and I've looked at many of these mini dumps. And so in practice, there's just you don't learn anything that would be any user secret.
I think we're done with most of the questions, so I'll just add up a couple more, I guess, from the top of my head. Or we can do it later in the discussion zone. Depends on what our time situation is.
I think we still have 10 more minutes.
Okay, so now imagine like you work for, let's say, a big company like ThinkCell, and there's probably like a guideline describing to everyone how you should handle errors within your entire code base. So one approach is to return error codes as the return value of most functions that can fail. Another approach is to pass a reference to error code, like some STL functions do. I guess like STD file system probably has overloads like this. Another approach is just to throw. And in some cases, you just terminate. What's the guideline like at ThinkCell, and which kind of strategy do you recommend?
Right. So, I mean, first of all, we distinguish, as I pointed out, we distinguish very strongly between defined behavior and undefined behavior. So, in case of undefined behavior, so you're encountering a problem that you did not expect, that you consider a critical error, like an API call that you don't expect to fail, suddenly fails, or an assertion gets violated. You don't deal with it. If that leads to a termination of the program because you have a null pointer access, if you are then inadvertently throwing an exception that you should not throw, the program gets terminated, and that's not for you to handle. Unless you decide, okay, it's defined behavior. So if you never spend any time on undefined behavior, you have to say, well, okay, if an error happens, and then so far it was undefined, and I have to handle it, then you basically make a defined behavior. You suddenly say, okay, no, the file doesn't have to be there, right? So any user can delete a file, so the file could be gone, and then this file gone is defined behavior. We don't discuss what you do in undefined behavior cases. It's meaningless to say I'm going to throw an exception or I'm going to return an error code or whatever. This doesn't happen. We don't write code for that. So any error that actually is returned from a function that you yourself wrote is actually for defined behavior. There's no distinction essentially between an error and a non-error. It's all just an output of the function. Now, how you transport this output out is, in a ThinkCell, entirely up to you. It's determined by the practicality of your code. Sometimes exceptions are practical. Sometimes you want the exception behavior because you have a large block of code and it's easy to make it exception safe and you want that these invisible code paths, they're nice, they help you in writing concise code. Then by no means write exceptions, right? And I have no qualms with it. In other cases, maybe you want a return value because exceptions are slow when they're thrown, and if something happens quite frequently, then maybe we don't want an exception because it would hurt performance, and in that case, we just use a return value. So these things in practice we decide pragmatically. It's a C++. You can use all the features of the language that you like. The main focus of the talk here is just make a conscious decision whether something is supported or not supported. And once you decide, okay, it's supported, then you can support it in whatever which way you want. You just have to write correct code. But don't just jump into an error handling code just because some documentation says this API function could throw an error. And in practice, it will turn out that it never does. By all means, if it does throw an error, you have to handle it, and then you handle it properly, and you can have all tools available to do it. But first, make sure that it actually throws, that it actually causes an error, that it actually is worth actually handling before you write any code for it.
Well, it's great to have so much flexibility, and I hope and I believe like all of the developers that are listening right now and work in your company and my company do conscious decision every time there's a chance the function can go wrong. for a heated discussion of on a topic of how we do it in practice, or maybe let's say exceptions versus multi-threading, global states, bus corruption, and stuff like that. I invite everyone to the Zoom discussion that's coming right after this, and I guess we can wrap this up.
All right, thank you very much.
Thank you too. Bye-bye.